This is the video for the final exam, day 1, and this is the second part in that series. So we're looking at problems numbers 10 through 18. We're going to start off with number 10, and it says, for the following function, find the domain and sketch the graph. So when we look at a function and they ask us about domain, we should kind of look for characteristics of what type of function is it. I see a square root symbol here, which tells me that I'm going to have a restricted domain because we can only allow the values that would keep our function to be a real number. So because square roots can have imaginary solutions when they have a negative underneath them, we need to make sure our domain keeps that inside of that radical, that radicand part, greater than or equal to 0. So we can actually do that first. Let's go ahead and list our domain. So the domain is that the part under the radical, which is x minus 3, needs to stay greater than or equal to 0. We'll solve that for x. So our domain, if we write it in interval notation, would be a bracket 3 to positive infinity. So we know our domain now. That's part of the question. The second part said we want to sketch the graph. Now, we learned in a section during the first part of the semester about how to do transformations of parent functions. And the parent functions were functions that we easily knew the shape of, or we could easily find them using a table of values. So the parent function for this guy would be square root of x, because that is the symbol that we see in this problem that looks like we have transformations built around that. So what we normally would do first is to do a little graph using our key points for the square root of x. And if you don't remember those, you can always make yourself a little table, again, making sure you're careful with domain here. You can't plug in a negative number. So we'll have 0, and let's do another perfect square is 1 and 4. That should be sufficient for graphing this. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. And we're getting those numbers by just plugging them into this parent equation. So if I plot that, I have, and I'll do that in a different color so we can see it, 0, 0. Let's put some marks on our graph. We also have 1, 1, and 4, 2. Okay, so that's the parent function. Now, looking at what we were given here, I see the following different types of transformations. I see a horizontal shift because we have adding or subtracting underneath the radical symbol. I see a vertical shift because we have something added or subtracted at the end of the function. And then I also see a negative in front of the parent function. That indicates a type of reflection. So when you're going to graph these, you want to do them kind of in the order of operations if you were evaluating. So I'm going to do the horizontal shift first because that's closest to the x. It's what's happening if we were evaluating. We would do that first. Then we would take a square root, and then we would multiply by that -1. We'll do that reflection second. And finally, we would subtract the 4. So I'm going to follow the order of operations when I do my graph. Now, when you have a plus or minus inside or underneath your function, your parent function part, so the part that was the parent, that means you're going to be shifting either left or right. And when it and it's also affecting the x value when we look at it on how it's affecting our table of values. So we're going to be shifting this in a direction for x. And the way we do this is we think about what would we need to kind of zero this back to its center, and that would be a +3. So it's the opposite of what we think here, the opposite operation. So this is going to be right 3. And then when we have a negative in front of our parent function, that is a reflection over the x-axis. And that actually is affecting your y value, your sign of your y in your table. I should have wrote x-axis, sorry. Talking and writing doesn't always work. And then this one is a shift down 4. And that's a vertical shift. So we know what we're doing for each of our transformations. So let's see if we can plot them using our, and I like to do it in steps. So we're going to do our steps here. So number 1, we need to move right 3. Right 3 means add 3 to our x values. And you could do that just by actually physically moving your points, or you can do it on your table. I'm going to do it on the table because I think that that helps you see the visual behind each thing. And instead of just getting one final answer of moving all the points. So right through 3 means we're going to add 3 to all of our x values. So you're going to take your chart and you're going to take each of the x values and add 3 to it. That'll be 7. Nothing happens to the y's in this step. So when we look at this, and I like to highlight this, write 3, change this part. Step 2, we're going to be doing our reflection over the x-axis. And what that really means is that your y's are going to change signs. They're going to flip upside down or right side up, depending on where they were, over the x-axis. So their y value is changing, but their x value is not. So we're going to take our chart that we just built off of. You want to keep this chart right here. This time, nothing's going to happen to the x's. That's a 4, by the way. But this time, we're going to change the signs of all the y's. So that's still going to be 0 because you can't change its sign. It's neutral. And then this will be -1 and -2. So reflected over the x-axis. That was the change there. And then finally, and this is where I'm going to add my graph underneath because this will be our final part of the transformation, we need to shift down 4. That means we're going to subtract 4 from our y's. Again, from the table we just built. So that's going to be 3, 4, and 7 haven't changed again. This will be -4, -5, and -6. So we're going to graph these 3 new points. This is our final setting. We've done all the transformations in the order of operations. And we're going to graph that on a new graph. I believe in the answer key, it's graphed on the same graph. I just like to show my work separately, but of course you can graph it on the same graph if that's part of the directions. Okay, so I need to get all the way down to -6. So we have the following points. We have 3, -4. So over 3 to the right, down -4. We have 4, -5. And then we have 7, 1, 2, 3, 4, 5, 6. Oops, need to add 7 in there. Down to -6. Ah. And hopefully you won't be drawing this on your test with a stylus, because those sometimes make it really hard to draw nice curves. That's the best I can do with that guy. So this is our final answer. This is the graph. This was the domain. We've done both parts. Okay, let's look at number 11. 11 says graph the piecewise function below. So a piecewise function is a function that has different pieces, essentially. So, and there's a domain that is given to you for each of the pieces. So for example, we're graphing a parabola, has an x squared in it, when our x's are less than or equal to 0. And we're graphing a linear equation or a linear function when we have x is greater than 0. So there's different ways you can do this. Some people, use transformations and then they erase and graph this whole parabola and then erase the part they don't need. And then they'll graph a line, use the, that you don't really need transformations for that, but then they'll erase the part they don't need. I prefer to do it by tables and split it based on the domain restriction. That's just personal choice. Doesn't mean it's right or wrong to do it a different way. But we're going to write out the 2 functions. So we have f of x equals x squared plus 3 when our x's are less than or equal to 0. So 0, -1, -2, just pick a few points that you can get enough to graph it. And then we're going to use f of x equals 3x minus 1 when x is greater than 0. Now, this may seem weird, but we actually do need 0 here. Even though it doesn't say equal to, the 0 is the splitting point of the graph. You shouldn't have a gap on your x-axis because it's stopping and starting at the same value. It's just including it as an endpoint on one of those sides and not including it as an endpoint. So it's really the difference between an open and closed circle. If you started with 1 here, you'd be missing all the decimals between 0 and 1. So we are going to use 0 here, even though it's not equal to, but we're going to make sure we make a note that this is going to be an open circle because it's not included when we graph it. And this endpoint is going to be a closed circle. That's the only difference between the two. Okay, so now we're going to plug these into our functions. So 0 squared is 0 plus 3 is 3. Negative 1 squared is 1 plus 3 is 4. Negative 2 squared is 4 plus 3 is 7. 3 times 0 is 0 minus 1 is negative 1. 3 times 1 is 3 minus 1 is 2. 3 times 2 is 6 minus 1 is 5. So we're going to set up a graph. And actually, I'm going to erase that first tick mark. It's kind of, oops, erase my whole thing. That one was kind of a little too close to the origin, not as nicely spaced out. And of course, you would probably want to use gridded paper. There are graph papers provided for you usually on the exams, or on your scratch work, you can print those off. So 0, 3 is going to be our first point that I'm going to plot for the parabola side. And I'm going to do that one in, I'll do color coding here. So I'm going to do this one in blue. So 0, 3 is right here. And this one is a closed circle because we are allowed to equal 0 here. Then we have negative 1, 4, and negative 2, 7. And this is a parabola on this side. And it does go on forever. We could keep picking x's because it's any x that's less than 0. So we could keep doing that forever. For the other side, I'm going to do that one in red. So we have 0, negative 1, which is an open circle. So notice I'm leaving that as an open circle. We have 1, 2, which is just a point, and 2, 5. And this side is a linear equation. And it does also go on forever because we can keep picking any x greater than 0. So that is how you can graph a piecewise function. If you had 3 lines here, if it broke into 3 pieces, you could do 3 separate tables. Okay, so let's move on to number 12. For number 12, we're taking this function, which is a quadratic, and we're going to put it in vertex form. And there's a reminder here of what vertex form should look like. It's f of x equals a parentheses x minus h squared plus k, where h and k, remember, are the vertex of your parabola. And the reason that works that way is because that's really transformations of functions. This is for however much we move right or left from the origin and then up or down. So the way we do this is that we use completing the square. So we're going to take the function and we're going to try to do completing the square all on one side. So it works a little differently than when we were solving equations. You're going to kind of ignore the minus 4 and move it to the end of what we're working with because it's keeping us from factoring this nicely the way we want to in a perfect square trinomial. And we also know that when we complete the square, we have to have a 1 in front. So we're going to pull the 3 to the front of the pieces that have the x in them. So that's going to be an x squared and then a minus 2x. And then we're going to leave a blank for ourselves to complete the square and create that perfect square trinomial that factors into the same binomial twice. Remember, that was the whole purpose behind completing the square. And then we still have our minus 4. It's not gone. But then whatever we do right here, we have to somehow counter it out here. Because if we're adding something to this side of the equation, normally we would also add it to the other side. But we want to keep f of x just over here as the function notation. So whatever we end up doing here, and that is going to include what's going on with this 3 because it's been pulled to the front, we want to make sure that we counter it with the opposite here because we want it to be like we added 0. So remember, when you're taking this and trying to figure out what to add here, we take half of the middle term and then we square it. So that's negative 1 squared, which is 1. So I'm going to be adding 1 inside my parentheses, and that will make that trinomial factor into the same binomial twice. Now, what I really did, though, was a 3 times a 1. Because this 3 out front was pulled out before we added this. So we actually added 3. To counter that, we're going to minus 3 on that outside part. If you were to distribute this back through, then we should be able to cancel those two terms out and go back to our original trinomial up here. So the whole purpose of doing this completing the square was that this now factors nicely into x minus 1 times x minus 1, which is x minus 1 squared. And then we have our minus 7 because we combine our like terms at the end. Now, if we were to ask you for the vertex, it wasn't in the directions, but we could ask you for that. The vertex is 1, negative 7, because it's opposite of what you see in here. Remember, shifting to the right, essentially, and then down 7. So exactly what we see here. Now we are asking you to sketch this or graph this function. So having the vertex is actually really useful for that. So I'm going to take this and I'm going to go over and plot it. So positive 1 down 1, 2, 3, 4, 5, 6, 7. There's my vertex. Okay, so positive 1 down 7. Another nice point to get, because you need at least 1 point on each side of your axis of symmetry, which remember is the part that goes through the vertex. I would usually plug in 0 and find my y-intercept if I haven't already plotted it. So maybe do a little table over here. And I'm going to plug in 0 for that. And that's going to give me 0, 0, and then negative 4 if I plug it in. So f of 0 is negative 4. You might also want to plug in maybe positive. Well, we know what positive 2 is going to be. Those are going to be symmetric because they're both 1 away from the center. So say we wanted one other point. Maybe we want to know what happens when we plug in negative 1. And I like to do this just because I like 5 points when I graph my parabolas. It makes them a little bit better and easier to shape. So if we plug in negative 1, I'll show the work for that one. It's a little more involved. That'd be 3 times negative 1 squared minus 6 times negative 1 minus 4. That is negative 1 squared is 1, so that's going to be a 3 plus a 6 and then minus a 4. So 9 minus 4 is 5. So let's plot these other points. So 0, negative 4 is here, and negative 1, 5, 1, 2, 3, 4, 5 is here. And notice that I should have symmetry around my vertex. Sometimes I like to put a V to mark the vertex. This point is the same distance away from the x value of our vertex, so it should have that same y output. And this is 2 away, negative 1 is, so we should have at 3, we should have the same value again. Remember, parabolas have symmetry related to the vertical line, which is called the axis of symmetry, that goes through their vertex. So there is our graph. Okay, let's talk about number 13. Number 13 gives us two functions, f of x and g of x, and they're both rational functions. We want to add them, subtract them, multiply, and divide them, and then state the domain of each. Now, it's helpful at the beginning if you already know your domain restrictions for each function. This one we cannot plug in a positive 2 because that would make us divide by 0. And this one we can't plug in a negative 4. So we're going to write out what does it mean to add the two functions together as our first step. So that means we are literally adding f of x plus g of x. Now, when you want to add two functions together, they have to have certain characteristics if they're rational. They're going to have the same denominator. So since we currently have different denominators, we're going to multiply each one by the other denominator to get that LCD. So I'm multiplying each one by, and we have to do it on both numerator and denominator because that's like multiplying by 1. It keeps it balanced. So then when we work this out, this is going to be x squared plus 4x. Be careful here. I always kind of highlight this. When you go to distribute for the second team, the plus sign has to get distributed with it. So this is going to be plus 3x squared, and then that'll be a minus 6x all over x minus 2, x plus 4. Add our like terms on the top. That's going to be 4x squared minus 2x all over x minus 2, x plus 4. And we could check to see if anything's going to reduce. If I pull a 2x, this is just my scratch over here. If I pull a 2x out of the top, I'm going to leave me with a 2x minus a 1. So technically, you don't have to do this step if it doesn't cause a cancellation. You can leave the top unfactored. But if, say, we pulled this out and we got an x minus 2, we would want to do the factoring step because it helps us reduce down our fraction. So that's the answer for that portion. And we'll come back and do the domain for these at the end. So let's now do f minus g. F minus g of x is going to work very similarly, except we're going to have a minus sign in between our two functions. That is going to matter when we go to do the distributive property in just a second. But essentially the same steps because we do need that common denominator. So be really careful right here. That's a negative 3x when we distribute it. So the first part's going to stay essentially the same. It's going to still be x squared plus 4x, but then we're going to get a minus 3x squared and a plus 6x. All over x minus 2, x plus 4. Add our like terms on top. That's going to be negative 2x squared plus 10x over x minus 2, x plus 4. I'll still come over here and check just to see if I pull out a negative 2x, that's going to be an x minus 5. So close, but not really. It doesn't match any of the binomials in the bottom. So that's good enough for our final answer. Now, when we get into multiplication, we don't have to get a common denominator, and neither do we have to do that for division. Because when you're dealing with multiplication and division, the rules are not the same. It's not about having a common denominator. When we multiply two functions together and their fractions, we do numerator times numerator and denominator times denominator. So I'm going to write this out as times. So numerator times numerator, it would be 3x squared over, and then we don't need to FOIL this out. You can leave it in factored form, just like the other ones were. And there's no like terms on top, so that's the end of that one. So actually multiplication is much easier than the adding and subtracting when we're doing rational functions. Now, when you go to do your division one, I always caution my class to put that in what I call the stacked format. Place f over g. We know that we're going to end up multiplying by the reciprocal because we don't divide with fractions, we multiply by the reciprocal. But having it in this format really will help us with the domain in just a minute. So then I would say, okay, we don't really divide with fractions, we multiply by their reciprocal. So that's going to flip that denominator's fraction and numerator, so it's going to flip them in the opposite direction. And then we can actually reduce here because there's an x in both of these monomials. So this ends up being x plus 4, and you can leave this as 3 times x minus 2. You could distribute that as well, but we haven't done it on any of the denominators. So when we get to this point, we're ready to talk about the domain of each. The domain of add, subtract, and multiply is always the same when we're doing these function combinations. And it's just what do the domains of the two functions have in common? In other words, if you wrote the interval notation for both of these, where would be the intersection, the common shaded regions of those two? So with rationals, it's pretty easy. You end up throwing out both of the denominator values that cause problems. So this would be our domain is any x in the real numbers as long as it's not negative 4 or 2. So that goes for all three of those. The quotient or the division part is a little bit harder because when you stack it like this, you're actually creating a complex rational expression. And with those, we have to make sure that we don't divide by 0 in any denominator. So this is an issue and this is an issue. Most people can see those right away because they are in the denominator of the little fractions. But also, this numerator in this stacked setup is in the denominator of the large fraction, the one that has this large division bar. So we actually do need to add another element. We need to throw out 0 because 3 times 0 would be 0. So we have to throw out an extra value when it's rational functions and there's an x in that numerator in the denominator of the big fraction. So that would be x cannot equal negative 4, 0, and 2. So that's the domain of this portion. F over g of x. And this was the domain for add, subtract, and multiply. Okay, let's move on to number 14. Now, number 14 and 15 are similar. It's just they don't tell you exactly what you're doing in both of them. This one's very specific and it says composite functions, F with G inside and G with F inside. But that's what this symbol means as well. This open circle, that it's not a times symbol. If it was times, we would just put them side by side. This is a composition symbol. This actually means F of G of X, which means G of X is the interior portion of the F function. And this is G of F of X. So these are both asking us to do the same thing. It's just recognizing those directions. So when I do these, I like to color code. So I'm going to let F of X always be red and G of X always be blue. So this first one says we're doing F with G inside as its input value. So when you've got it set up like this, you go to the outer function first, and you actually say, okay, I need to know what F looks like before I can plug G into it. So I like to read it as a function that has no X at the moment. So that's going to be square root of blank plus 7. And then that blank is where the X used to be, our input value. So our new input value is now G of X. Well, G of X is the function 3x squared minus 2. Once you've got the composition set up, you're just simplifying. So we can just add that 7 and the negative 2 together. Can't do any simplifying here because this is a binomial. You can't take a square root of the individual pieces. So that is the final answer for that way. Then we want to do G of F of X. So G function with the input being F. So I go to my G function first and I say, okay, I need to know what that looks like before we plug anything into it. So that's 3 blank squared minus 2. The input is my blank. And then I'm plugging into the input the F of X function. So that's going to be square root of X plus 7. Now, when you're simplifying this one, the square and the square root are inverses of each other. They cancel each other out. So we're just going to get 3 times X plus 7 minus 2, and we do want to work that out. So that's going to be 3x plus 21 minus 2. So 3x plus 19. So there's my composition both directions. All right, the same thing for 15. I'm going to color code it. We'll let F be red, G be blue, F of G of X. Let's work on that one first. So the F function is 6 blank squared minus 5. The input for that now is going to be 4x plus 7. And this one's going to require a little bit of work to clean it up. When we see a binomial squared, we need to write it twice and FOIL it out, or distributive property if you don't like to call it FOIL. So that's going to be 16x squared plus 28x plus another 28x plus 49 minus 5 at the end. We need to distribute, actually I'm going to add the like terms first. So 16x squared plus, that's going to be 56x plus 49 minus 5. Get my handy calculator out. So 6 times 16 is 96 x squared. 56 times 6 is 336 x. 49 times 6 is 294. And then we have that minus 5 at the end. So we're going to go ahead and subtract 5 from the 294, and that gives me 289. So there is the simplified down version of f of g of x. So let's now do g of f of x. And the funny thing is, when you're doing compositions, usually one of them will be much quicker than the other. So g is 4 blank plus 7. And then the blank we're going to fill in, that input is now going to be 6x squared minus 5. Notice this one's going to evaluate much quicker because there's no squaring happening to the piece that we inputted. So this is just going to be 24x squared minus 20 plus 7. So that's 24x squared minus 13. Much quicker to evaluate and simplify down. Okay, so I believe there were no domain questions on either one of those. So we're ready to move on to number 16. This is sketching a polynomial function and also talking about when is the output or f of x value, the range, greater than 0, so kind of above the x-axis, and when is the output value going to be less than 0, which means below the x-axis. So when are our y's greater than 0 and when are our y's less than 0? And that's a reference to the x values, the domain values that happens on. Now, when we're graphing or sketching these polynomial functions, you can do a sign chart. That is one method, but we like to do it by end behavior and multiplicity because that is a skill that will be helpful in future classes. So when you look at a polynomial function, and I always do a little chart, this is kind of the end behavior review. Put it up here so it's not in the way. You could have a leading coefficient that is positive or negative. So my leading coefficient can either be positive or negative. Oops. And I could have a function that has an odd degree up front as our leading power once we have it in descending order, or it could be even. Okay. Now, evens behave a lot like parabolas, like x squared. So if you have a leading coefficient that's positive and your highest degree is even, then you're going to have two end behaviors where they go up towards positive infinity on the y values forever. And that happens as we go to the negative infinity on the x-axis and the positive infinity on the right side of the x-axis. So we're going up forever for our y values. If you're even and you have a negative in front as your leading coefficient, it just reflects it over the x-axis, essentially, those pieces. So it flips both end behaviors down. If you have an odd with a leading coefficient that's positive, it behaves like x cubed. So it's going to be down on the left and up on the right. If you change the leading coefficient to negative, that just flips which one is up and which one is down. So that's a kind of a little reminder chart of what's happening when we look at end behavior. And then we also look at the multiplicity of each x-intercept, and we talk, or the zeros as we like to call them. And we found out in class that that meant that they had a specific behavior at the 0. So that's the pieces that we need to be able to graph this. So I'm going to look at my first function here, and I'm going to list out what I know about the end behavior. So in behavior, I need to know the leading coefficient, and I need to know the degree of the polynomial. Leading coefficient is always attached to, if you're in descending order, it's in front of your highest degree. So that is a positive. And then the highest degree is also odd. So that means that I am down on the left and up on the right. And that's going to be important to us when we go to graph this. Then we want to talk about the multiplicity behavior, the behavior at the zeros. And multiplicity, just remember, means how many times does a 0 occur. So when we want to find the behavior at the zeros, we actually have to find our intercepts. And that's going to require us setting our function equal to 0 for the y value. Our f of x essentially becomes 0. And we try to factor this. So I'm going to pull out an x squared. That's going to be x plus 4. I'm going to pull out a minus 1 since this leads with a negative. That's going to be x plus 4. I get x plus 4 is a common binomial, and that leaves me with the leftovers of x squared minus 1, which factors again into the difference of two perfect squares. Square root of x squared is x, square root of 1 is 1. So we get an x plus 1 and an x minus 1. That means I have zeros at -4, -1, and 1. Now I make, and I jokingly call this my zombie chart. That's just my little device to help me remember it, but it's the zeros, the multiplicity of that 0, and the behavior at that 0. So I always put these in order from least to greatest because that helps me when I go to graph it, and they ended up being in that order just coincidentally right here. And then you look at the exponent, or how many times each factor occurred. That helps you know your multiplicity. So all of these had a multiplicity of 1. I like to write that as a word, the number 1 or the number 2 or the number 3. I actually write it as a word so that I don't get confused and think that these are ordered pairs. Because remember, these are on the x-axis. And then when you have your behavior, we learned that if it is an odd multiplicity, it's going to have the behavior that it crosses the x-axis at that 0. If it has an even multiplicity, so like squared or the 4th power, it's going to bounce or touch. That's usually the word they use in the textbooks, is that it's gonna look a lot like a little parabola there, like it's touching that x-intercept and bouncing back. And there is a difference between a 1 and a 3, 5, 7, like all odd numbers that are 3 and higher, those exponents. If you have a 1, you cross more like a line, like a y equals mx plus b line there. If you have a 3, 5, 7 or higher odd number, you cross more like x cubed. You have that little kind of behavior where it kind of almost looks like it's going to even off, but it goes. So that's just something to be aware of. Now, the behavior for these is all 1, so we're just going to be crossed like a line. Okay, so once you know all of your pieces, you're going to go over to your graph, and we're going to place those x-intercepts down first. I'm not going to put any values on my y-axis at all, because when we graph these, we're doing a rough sketch. We're looking for behavior only and getting the right pieces where they're supposed to be. We have no way of knowing the highest or lowest points on each of the little terms of the polynomial. That would require some calculus. So we're just doing a general sketch. So at -4, I'm going to do this in the purple color. We have an x-intercept there. We have one at -1, and we have one at +1. The next part is really important. You want to put your end behaviors down next, because that determines how you go through from left to right. So the end behavior is supposed to be down on the farthest to the left x-intercept, and at the farthest x-intercept to the right, or 0, we would go up. Then we read our chart as we go. At -4, the behavior was 1, which means cross like a line. So we were below the x-axis, so we're going to cross up and above. Now we can't go up forever or go up and do fancy little things, because eventually we have to come back down and actually touch this x-intercept. At the next x-intercept, our behavior or multiplicity was a 1 again, so still crossing through like a line. So we cross the x-axis down into the lower area. And then at our final one, we don't know where the turn really happens, just do your best judgment. We are going to cross like a line again. So if you've done this correctly, your end behavior should match up with the pathway that you've chosen to go using your 0 multiplicity behavior chart. So once we have our graph down, we had one more question. They asked us to find all values of x such that f of x is greater than 0 and f of x is less than 0, and we have our sketch. So this part is part of my answer. But when I ask when is f of x greater than 0 and when is f of x less than 0, we're asking you to look at the actual x-axis and say what are output values and what x values are coordinated to those. So if you notice, I'm just highlighting this a little briefly. From -infinity up to this actual x-intercept, all of my y values before that point were all negative. So that puts it in the less than 0 portion. So from -infinity to -4, every x value in this interval is giving a negative y value. And then from, and you don't have to have the highlighter part, this is just to help you visualize, from -4 to -1, all of those x values have a positive y output. So from -4 to -1. Then from -1 to 1, we're back to having negative y values again. So we union that. And then for the remainder of the graph, from 1 on, my y values always come out as positive. So 1 to infinity. So these x values in those subintervals produce y values that are either positive or negative. And we do not use brackets on those answers because we are not including the equal to 0. So that's why the x-intercepts do not have brackets. All right, so let's do another one very similar to this. This one is already pre-factored for us. That's going to make the zero part easier, but it actually sometimes makes the end behavior a little harder to look at and set up. So remember, for end behavior, we needed to know our leading coefficient sign. Was it positive or negative? And we also need to know our degree being either even or odd. So you can still look at up here and see that, you know, all of these have been factored, and this leading coefficient up front, if we were to redistribute all this, we would be distributing that and it would affect that leading coefficient. So our leading coefficient is negative here. Now, when you have it pre-factored, if you want to know your highest degree, one way of knowing that would be to FOIL all this back out, distribute it all back out, and then see what the highest power is. But if you just think about each individual piece, if I was to work this out, the highest power I'm going to get from this portion is an x squared. This is just going to be an x to the first, and this is an x to the third. So we're multiplying those three pieces together. So x to the third times x to the first times this one would give me an x squared. You're really just adding those multiplicity exponents there. Now that could change if there was a square inside here as well, because that would make this bigger when you FOIL or distribute it out. So I always just kind of tell students to check this highest power here. If I worked it out as squared, highest power if I work this guy out as 1, and then this one's cubed by itself. So when we add up the exponents, when we multiply that highest term together for each part, we're going to get 3 plus 1 plus 2, which is x to the 6th, which is even. Okay. So if you're even, your end behaviors head in the same direction, and negative means they're both heading down to negative infinity. All right, so now let's talk about our behavior at our zeros. So we already have this factored, so it's going to be really easy to pull those zeros out. I like to put the 1 for emphasis, so it helps me with my multiplicity. This guy would be 0 when 0 is in there. This one would be a positive 5, and this one would be negative 3. We're setting those equal to 0 individually and solving them using the factor theorem. Now, on my chart, the negative 3 would be first because it's the smallest, and I always graph from left to right. 0 is the next largest, and then 5. Multiplicities. Now, you have to look at the correct one. Negative 3 came from this factor, and it has a multiplicity of 2. Notice again, I'm writing it as a word, not a number. 0 came from this factor. It has a multiplicity of 3. And then 5 came from the middle one, which has a multiplicity of 1. So all three of these are different. This is going to be a touch or a bounce. That's how I like to think of it. A 3 is going to cross like x cubed. All odd powers 3 and higher, like 5, 7, 9, they all cross like x cubed. And then if you have a 1, it is still odd, but it'll cross like a line. Now it's hard to distinguish and draw the cross like x cubed, but it's nice to know if you can distinguish and see that. So let's do our graph. We're going to place our x-intercepts first. So negative 3, 0, and positive 5. I might do those in a different color so that they stand out. Okay, end behavior is down on both sides, farthest x-intercepts from each other. At negative 3, we're supposed to touch or bounce. That means you're going to stay in the same region of the y values that you are right now. So my y values are negative, so we're going to stay negative. We're going to bounce back down into this negative y area. At 0, we're supposed to cross like x cubed. So I'll do my best to draw that. So you notice I kind of tried to make it look like an x cubed there at 0. And then we go up because we crossed, and then we start heading back eventually at some point. We don't really know where that happens without calculus. And then we're going to cross like a line. Okay, so this is our rough sketch of that graph. Now let's do our when are we above, when are we below. So, and I won't write all the highlighter this time. So from negative infinity to, and you do need to split this here. I know this stays negative y values for this whole area right here, but we do equal 0 at that point, and we're not allowed to equal 0. So this is going to be from negative infinity to negative 3. We have y values that are negative. From negative 3 to 0, we still have y values that are negative. From 0 to 5, our y values are positive, and from 5 to infinity, our y values are back negative. So there is that piece. Okay, we've made it to the very last problem for final exam, review day 1. This is find the quotient and remainder if we're taking the polynomial 2x to the 4th minus 8x cubed plus 12x minus 17 and dividing it by the binomial 2x squared plus 6. So when we look at doing these types of problems, the first question is, students are usually like, oh, I've learned synthetic division. Can I use that? No, you cannot, because synthetic division is only usable when you're dividing by an x to the first term as your highest power, and ours is x squared. So we're going to have to do long division. So we're going to place 2x squared plus 6. If you want to put a placeholder for 0x here, you can. That's not as important as putting the placeholder on the part you're dividing into. We want to make sure any missing powers here, we want to go from descending order, and any missing powers are accounted for so that when we line up our terms, everything works out nicely. So we are missing the x squared term. So when we miss a term, we put in a 0 times it. So that means it's really not there, but we're using that as a placeholder. Let me write that better. So that's 2x to the 4th minus 8x cubed plus 0x squared plus 12x minus 17. Our first step is to ask, what would I need to multiply 2x squared by to make it 2x to the 4th? Well, it already has the 2, so it just needs an x squared. And I always place that above the same like term column. That's going to help us keep everything lined up. And it also tells you have about 2 more rounds of division to go. Once you've placed your number up here, I always do a little scratch work out to the side. You're going to multiply that by everything out front. And when we do long division, we change the sign. We subtract that. Remember, we're trying to figure out how much would be left over. So I always go ahead and put that here so that when I write this over, I've already taken care of the sign. So that's negative 2x to the 4th and a minus 6x squared. So we're going to take that and make sure we write them under their like terms. Okay, then we can combine all of our columns together. So this is going to cancel if we've done that correctly. We're going to bring this down. This is negative 8x to the 3rd. We have a minus 6x squared. Bring down our plus 12x and our minus 17. Okay, round 2. What do I multiply 2x squared by to make negative 8x to the 3rd? Well, I would need to multiply by a negative 4, and I need another x. So when you go to do this piece, you're only going to be multiplying this negative 4x by everything out front. So negative 4x times 2x squared plus 6. And this is why I used a different color on this line up above. We're going to change that sign to a plus because it's minus whatever we have here. So if it's already negative, it's going to be minus minus. It changes to a plus sign. So this is going to be 8x cubed and plus 24x. Line those up underneath their appropriate columns. This is going to cancel, bring this down, and this should be our final round of division. So we're looking at 2x squared multiplied by what makes negative 6x squared. Well, it looks like we've already got the x's worked out. We just need a minus 3 to multiply by all of that. So minus 3 times 2x squared plus 6. Again, we're doing long division, so we're going to have to change the sign because we're subtracting to find out what's left over. So that's going to be 6x squared plus 18. Line those up and go through. This cancels. This is 36x and plus 11. All right. Oh, I actually messed up. Hang on just a second. It's good that I caught that before I ended the video. When I was bringing this down, I lost my 1. That makes a very big difference down here. That was a 17, so it's very easy when I use the pen stroke. I might have written it here, but it got deleted. This was a minus 17 that we're bringing down all the way across. So that actually makes this just a positive 1. So our quotient is what, how many times did we go in evenly, essentially? So that's the x squared minus 4x minus 3. And our remainder is what's left over at the end. Now we know we can't divide anymore because this is an x squared, this is an x to the first. A bigger x cannot divide into a smaller x. So I'm glad I caught that error. So that's the end of the final review, day 1, part 2 of the video. Good luck on your exam. Make sure you study very hard.